In the last lecture, we looked at the various properties of Z transforms, and as the last property, we looked at the statement of the final value theorem, which in effect states that the discrete time function f n takes the last value or the final value of that, which can be written as f infinity, which is limit as n goes to infinity of f of n. It can be obtained from its Z transform by making the product 1 minus Z power minus 1 multiplying f of z and taking the limit of that function as z goes to 1. And this is true provided all the poles of this function 1 minus z minus 1 multiplying f of z are inside the unit circle. There can't be any pole either outside the unit circle or even on the unit circle. The proof for this can be given in the following manner. Suppose I write Gn as Fn Un minus Fn minus 1 multiplied by Un minus 1. Suppose I form a new function Gn which is Fn Un minus Fn minus 1 Un minus 1. It's obvious that G0 when n equals 0, this is f0 u0, that is f0, and because Un minus 1 is there, when n equals 0, that is going to be 0. G1 equals f1 times u1, that is f1, minus when n equals 1, this is f0, this is of course u0 is also equal to 1, this is f1 minus f0. G2 likewise can be shown to be f2 minus f1 and so on and so forth. So if you take the sum of Gn from n equals 0 to some value capital N, then you add up all these functions. When you add G0 to G1, you get f1. When you add G0, G1 and G2, you end up with f2. So it's obvious this is going to be Gn. That is, when you add up Gn, all the samples Gn from n equals small n equals 0 to capital N, this is going to be, Fn, this is going to be Fn. Fn. So from this analysis, you can see that f infinity, which is of course limit as n goes to infinity of f of n, is also equal to n from 0 to infinity of Gn, this function Gn. Now let us see how we relate f infinity now to the Z transform of f of n. From this definition of g of n, it's clear that g of z, the Z transform of that will be the Z transform of this minus the Z transform of this. The Z transform of this is f of z, and this is a delayed version of f of n, delayed by one sampling instant, 1 unit. Therefore this is z power minus 1 times f of z, which is really 1 minus z power minus 1 multiplied by f of z. That's what it is. G of z therefore is 1 minus z power minus 1 f of z. But what is the definition of g of z? G of z is Gn z power minus n, n from 0 to infinity. Right. Therefore, from this we can see that when you substitute z equals 1, z goes to 1 of g of z is equal to summation from 0 to infinity of Gn. Therefore, limit as z goes to 1 of g of z is the summation of the samples in time 0 to infinity of Gn, which indeed is what we want, that is f of infinity. And what is g of z? G of z is equal to this. That means this quantity is also equal to limit as z goes to 1 or 1 minus z power minus 1 f of z. So the upshot of this is that these two are equal. So f of infinity equals limit as z goes to 1 or 1 minus z power minus 1 f of z. Now, using this, in getting at this result, you have took the limit as z goes to 1. So this f of z, g of z, whatever we are talking about, should be valid for values of z within the region of convergence. That means z equals 1 must be within the region of convergence of the transform that we are talking about. In fact, 1 minus z minus 1 to the power of f of z is the transform gz. Therefore, gz should have the region of convergence which includes the point z equals 1. That means the unit circle must be within the region of convergence of g of z, and that is the condition why we said 1 minus z power minus 1 f of z, all the poles must be within the unit circle. And this is a very important condition, because if you don't pay regard to this condition, you may get wrong results. The final value theorem may not apply, but you may still get some value and assume that it is the final value. It may or may not be true. One can construct this proof in an alternative and perhaps a simpler fashion by saying, after all, we are talking about a final value for the sample train Fn. When will you have a final value? After all, when all the transient terms die out, you have steady state term, then you can think of a final value. If the steady state terms in f of n are sinusoidally varying or periodic samples, then there is no final value, because this will be oscillating forever. So the only way in which we can associate a final value with f of n is when it has got some step function as part of it, and there is no other periodic function. So if you have a step function in this f of n, and you want to find out in the partial fraction expansion of f of z, the residue associated with the z transform of the step, z over z minus 1, you essentially what you do is you multiply f of z by 1 minus z power minus 1 and take the limit as z goes to 1. And that is exactly the value of the step function that is embedded in f of n, and that is the final value. If there are sinusoids inside f of n, then obviously this condition will be violated, because when you multiply 1 minus z minus 1 f of z, you will have poles. If there is a sinusoid, there will be poles here and here. So this condition will be violated. Therefore, a final value will occur only when the only steady state function that is embedded in f of n is a step function, and the magnitude of the step can be obtained by partial fraction expansion by taking the limit as z goes to 1 of this, and that is the final value. So this is equivalent to this. Examples. Let us take first one example. Suppose we are given f of z equals 1 over z minus 1. Then 1 minus z power minus 1 times f of z equals 1. And this is a constant, certainly it is analytic, it has no poles on the unit circle and outside the unit circle, therefore it's well behaved. So limit as z goes to 1 of 1 minus z minus 1 f of z is of course 1, and since we know this is the unit step function, final value is equal to 1, so there is no surprise in our result here. Let us take a second example. Suppose I say f of z equals 1 over 1 minus z power minus 2, and it is further said that the region of convergence of this is z greater than 1. Now, since the region of convergence of this is the region outside the unit circle, I can expand this in powers of z power minus 1. So I can write this as 1 plus z power minus 2 plus z power minus 4, z power minus 6, and so on and so forth. So that means this f of z is associated with a discrete time function which has got this sequence of values 1 at n equals 0. The next sample occurs at 2 because there is no coefficient of z power minus 1 is 0. Therefore, at n equals 1 the sample value is 0. At n equals 2 once again it is 1. At 3 it is 0. At 4 is equal to it's 1 and so on and so forth. So every alternate sample is 1 or 0. Now let us see. Let us see whether we apply the final value theorem and see if we can get any result. Limit as z goes to 1 of 1 minus z power minus 1 times f of z is obviously limit as z goes to 1. When you multiply this you get 1 over 1 plus z power minus 1. And certainly a limit exists for this. When you substitute z equals 1 you get a value half. Right. But then this f of n that we are talking about is either 1 or 0, and when n goes to infinity you can't say what its final value is going to be. It's either 0, we can't say it is going to be 0 or 1, but the value you get a definite value as you take the limiting process is equal to half. The answer to this discrepancy is that the final value theorem does not apply to this case, because this function now has a pole at z equals minus 1. After all, 1 minus z power minus 1 f of z, this is equal to z upon z plus 1. So this function has a 0 here and a pole at minus 1. So 1 minus z power minus 1 multiplying f of z is not analytic, doesn't have is not analytic on the unit circle. So one should have that particular condition satisfied before you apply the final value theorem. So whatever result you got here is not in accordance with the actual situation. You may get some result that is actually you got an average between 1 and 0, but that is not the final value associated with this, because nobody can say what the final value of this is going to be. So after having considered the various properties of Z transforms, now it is time for us to see how we find the inverse Z transformation. So far we have talked about transformation of discrete time functions, Z transform and discrete time functions. Now we should like to see, given a Z transform, how you would recover the discrete time function from this, and this process is called the inverse transformation, and let us see what are the techniques available for us to achieve this inverse Z transformation. To find the discrete time function corresponding to a given Z transform, the process which is called the inverse transformation, the basic way of doing this would be through contour integration. Given f of z, you can recover f of n by using this formula along a closed contour C inside the region of convergence. Of f of z. So Z transform exists within a certain region of convergence. So if I have f of z having various poles like this, zeros and so on, so you take a closed contour, usually a circle, go around the contour in the anti-clockwise direction and do this integration. And those of you who are familiar with the integration in the complex variable situation, complex variables where complex variables are involved, you form this function, find out the residues of the various poles of this function inside this contour, and since we have got 2 pi j here, the sum of those residues will be your f of n. So this is a fundamental way of doing this, and one can also interpret this just as we have done in the continuous case as f of z. Suppose you take this contour f of z and suppose you take some angle theta here, delta theta, so f of z times delta theta over 2 pi z power n. This is the characteristic signal in the discrete time case, and this is the coefficient associated with this. So f of z delta theta over 2 pi is the coefficient. This can be called the coefficient density, and you can interpret this in a similar way as we have done in the Laplace transform. But we will not go deep into that. I just want to point out there is an analogy. Nevertheless, we will not pursue this contour integration because we very rarely apply for our work. Of course, if what we would like to do is more go by the partial fraction expansion, which I will talk about a little later. That is more straightforward than what we normally apply. But if we have some Z transforms which are not easily recognized as the Z transforms of known time functions, then one may have to go to this contour integration in a general case. This is more fundamental in general, but we rarely apply because we have simpler methods to achieve the same thing. So we leave it at that. A second and a very simplistic method is the series expansion. Suppose we are given f of z and you expand this in ascending powers of z power minus 1, then each coefficient of z power minus 1, z power minus 2, and so on and so forth defines the value of the sample at appropriate instants of time. Therefore, if all we have to do therefore is expand f of z as a series with the increasing powers of z power minus 1. And if you achieve that, then you know the values of the samples at different distinct points of time. That's what we do. So let us take an example. Suppose I say f of z equals a upon z minus a, and the region of convergence is I'll say omega, let us say omega, z greater than omega, or omega over z magnitude is less than 1. Therefore, we would like to expand this in powers of negative exponents, negative powers of omega over z. So for that purpose, I will write this as a upon 1 minus omega over z. So I will put a upon z here. A upon z 1 minus omega over z. So this can be written as a upon z to 1 plus omega upon z plus omega squared upon z squared, and so on and so forth. And this series converges to this because omega upon z magnitude is less than 1. And this is also in accordance with what we have for a single-sided z transform, where the f of z is defined as fn times z power minus 1. That means the expansion that we are looking for is increasing powers of z power minus 1. Therefore, this can be written as a z power minus 1, the first term, plus a w z power minus 2, the second term, plus a w squared z power minus 3, and so on and so forth. So you can see that as far as the time function which corresponds to the z transform is concerned, it must have a sequence like this. The first term is a power z minus 1. That means there is a 0 value at n equals 1, n equals 0. At n equals 1, the value of this is a. At n equals 2, the value of this is a omega. At n equals 2, 3, it is a omega squared, and so on and so forth. So from this you can conclude that f of n at the nth sample is a w to the power of n minus 1, and this sample sequence starts at n equals 1. It is 0 at n equals 0. Therefore, you must multiply this by u of n minus 1. That's what we have got. So that answers aw power aw power n minus 1 un minus 1. That is your f of n corresponding to this. So in this case, we observe that we have been able to get a closed form expression for your f of n. This may or may not be possible all the time. So let us now take a slightly more complicated example. F of z equals z upon z minus half times z minus quarter. So the region of convergence for this is z greater than 1/2. Z magnitude greater than 1/2. Now what we do is we make the long division. So the denominator is z squared minus 3/4 z plus 1/8. So this we divide into z. So first term will be z power minus 1. So z power minus 1 multiplied by this will become z minus 3/4 plus 1/8 z power minus 1. So when you subtract from this, you get 3/4 minus 1/8 z power minus 1. And that you divide this into this, so you get 3/4 z power minus 2, so that all the time the first coefficient is knocked out. So 3/4 minus 9/16 z power minus 2 times z, therefore z power minus 1, and then you have plus 3/32 z power minus 2. Subtract from this, this gets cancelled out, and you have 7/16 z power minus 1 minus 3/32 z power minus 2. And then you want again to cancel this out, so the next term will be 7/16 z power minus 2, and then that will be cancelled out, and so on. You can continue like this. So you observe that when you divide this denominator by this, what you get is a series like this. So this must be the z transform. This is equivalent to f of z expanded in ascending powers of z power minus 1 is equal to this. Therefore we now identify this with the z transform of a discrete time function. So the first sample occurs at n equals 1, because after all fn times z power f1 times z power minus 1 is the term that corresponds to f1. Therefore fn now can be thought of as a sequence of samples. There is no constant term, therefore n equals 0, the value equals 1. N equals 1, the coefficient is z power minus 1 is 1, therefore 1. N equals 2, the coefficient of z power minus 2 is 3/4. N equals 2, this must be, by the way, this must be at minus 3. Therefore n equals 3, the coefficient is 7/16, and so on and so forth. So this is how one can obtain the inverse Z transform by the long division method like this. A few comments on this. The long division method, of course, is simple and straightforward, and once we have the quotient series, we can identify the sample values with the coefficient of powers of Z as we have seen here. Method is simple and straightforward, not much theory is involved here. It is simple to implement, and we can carry this out analysis as long as we wish. We can expand this series to the desired length. We can terminate at any given point of time. So you can carry this long division to a length that depends upon your convenience. The point to keep in mind, however, is that this must be in expanding powers of z power minus 1, because we are talking about a unilateral z transform. Unilateral z transform is fn times z power minus n. N has positive values. Therefore, you must make sure that you are expanding it in ascending powers of z power minus 1. It is very convenient for numerical working of a problem. However, once we get a series like this and then corresponding f of n, you may or may not be able to find out a nice closed form expression for f of n. It depends upon your ingenuity and to some extent your luck. So there is no guarantee that you will be able to conveniently find out a nice closed form expression for f of n through this process. But this is convenient for numerical work. So the last two examples have shown how the long division method can be obtained to find out the inverse Z transform of a given function of Z. But as I mentioned earlier, it is the partial fraction expansion method which is the most favored method compared with the contour integration method and this long division method, and this is what we will take up next. By far the most common method of finding out the inverse Z transformation is the partial fraction expansion technique, Here, as we have done in the continuous time case, we are dealing with Laplace transforms. You break up the given f of z into simple terms, each of which is recognized as a z transform of a known time function, discrete time function. Principle is the same. So we will illustrate this by means of examples, because there is nothing much to describe about the technique as such. Suppose f of z is given as z upon z minus half times z minus 1/4. This is exactly the same expression that we took up when we are during the long division. So let us make the partial fraction expansion of that. So you have two terms, z power minus half and z power minus 1/4. So if you call that a and b, a is obtained by multiplying this by z power minus half. So once you multiply this expression by z power minus half, you are left with z upon z minus 1/4 and substitute z equals half. That is the same way as we did in the case of f of s in the Laplace transform domain. Same thing you do here also. To find the a corresponding to this, you multiply this by z power minus half and substitute z equals half. Therefore, this is half divided by 1/4, that is equal to 2. So b likewise is, you multiply this term by z power z minus 1/4, so z upon z minus half and substitute z equals 1/4. So this is 1/4 divided by 1/4 minus half minus 1/4, that is equal to minus 1. So a equals 2 and b equals minus 1. Therefore, this is 2 upon z minus half minus 1 upon z minus 1/4. So these are two terms which constitute f of z. So if you can find out the inverse z transform of each of these, their difference is equal to f of n. Now let us see. If I had z upon z minus half, I would have written this as half n un. Z upon z minus half is the z transform of a discrete time function which is half raised to the power of n un. But now instead of z I have 2 times 1. So 1 upon z minus half is the same as z minus 1 multiplying this z upon z minus half. After all, if you multiply this by z minus 1, you get this. Multiplication by z minus 1 in the transform domain is equivalent to delaying this time function by 1 unit. Therefore, this corresponds to half of n minus 1 u of n minus 1. So using that principle, you can write this as the inverse z transform of this f of n equals, as far as the first function is concerned, 2 times half raised to the power of n minus 1 un minus 1, and using the same arguments here, minus 1, half of, instead of half you have got 1/4 here, 1/4 n minus 1 un minus 1. Or we can put this as, you can leave it at that, that is okay. You can put n minus 1 as a common factor, 2 times half n minus 1 minus 1/4 n minus 1. So when you are making this partial fraction expansion here, when you have first order terms in the denominator, you have constant terms in the numerator, and therefore whenever a constant term by z minus half or z minus w is involved, un minus 1 comes into the picture. We would like to avoid this. After all, we would like to have a partial fraction expansion in terms like this, where we can easily recognize them to be, say, z over z minus w as w to the power of n un. So in order to have a partial fraction expansion involving terms of this type, we have to multiply this by z somehow, and to do that, it's convenient for us to make the partial fraction expansion of f of z over z. If you make the partial fraction expansion of f of z over z and then multiply z right through, you get terms like this. Therefore, let us do that. As an alternative, which is widely preferred, given f of z, you first form f of z over z. In our case, this is f of z. Therefore, if you divide this by z, you get 1 over z power minus half multiplied by z power minus 1/4. And let the partial fraction expansion of this be c upon z minus half plus d upon z minus 1/4. And you can, for c is of course, multiply this by z power minus half, 1 over z power z minus 1/4 evaluated when z equals half. And so you can work this out and show that this is equal to 4 upon z minus half minus 4 upon z minus 1/4. Therefore, we can now write f of z equals 4z upon z minus half minus 4z upon z minus 1/4. Now this is a form which is convenient for us to use. So f of n can be written as z upon z minus half is the z transform of half raised to the power of n un. Therefore, this is 4. 4 is a common factor right through. Half n un will be there, and here it is minus 1/4. Therefore, minus of 1/4 raised to the power of n un. So that is your f of n. You observe that this for the same f of z, you have got one expression for f of n here, which in terms of n minus 1 un minus 1, and you have got a new expression for f of n in terms of un. It can be shown that both are equivalent. If you take the numerical values from n equals 0 onwards, it turns out both are equivalent. Therefore, you have got apparently a seemingly different answer, but both our expressions are equivalent. Both are equal to each other for all values of n. And this is a method which recommends itself for most often, whenever we are given f of z, we divide by z right through and make the partial fraction expansion, so that we have a z term in the numerator, and z term in the numerator associated with first order terms is very convenient to handle. Let us take another example. As a second example, let us take a case where you have a quadratic term in the denominator, z squared plus z plus half. The poles associated with this quadratic term in the denominator are, so if you take z squared plus z plus half as z minus p1 times z minus p2, where p1 and p2 are the poles, you can show that p1 equals minus half plus j upon 2, which can be further written as 1 over square root of 2 e to the power of j 3 pi by 4. That is one way of expressing p1. And p2, because all the coefficients here are real, whenever p1 is a pole, a complex pole as here, p2 it must be accompanied by its complex conjugate. Therefore, p2 has got to be the conjugate of p1. Therefore, p2 turns out to be minus half minus j upon 2 or 1 over root 2 e to the power of minus j 3 pi upon 4. So you don't have to make any special efforts to calculate p2. So you can now, suppose I write this as k upon z minus p1, then since again all the coefficients are real, involved here are real, this will be z minus p1 conjugate. So p2 you don't have to write separately. If it's p1, that has got to be p1 conjugate, because there are only two poles, and if one is a complex pole, it must be accompanied by its conjugate. Therefore, it goes without saying that the other pole must be p1 conjugate. Not only that, if the residue here is k, the residue associated with this must be k star. Then only when you have a common denominator and work it out, you will have numerator coefficients all real, as it is in this case. Therefore, in finding out the partial fraction expansion for this, it's enough if you find out k conjugate, the other residue corresponding to z minus p1 star immediately follows. You can calculate the value of k. I will not work it out. It can be shown to be 1 over root 2 e to the power of j pi by 4. And now, therefore, you can combine this information with this k and k star, and you can write f of n as, I will not give the complete steps, the missing steps you should be able to fill it out. You can show that this will be equal to 1 by root 2 to the power of n e to the power of j n minus 1 3 pi by 4 plus pi by 4 plus e to the power of minus j n minus 1 3 pi by 4 plus pi by 4, all this times un minus 1. And again this entire thing can be simplified and can be put in the alternative form, 2 times 1 by root 2 to the power of n sine 3n pi by 4 un. This is the final answer. An alternative is, after all, I have made the partial fraction expansion of f of z, and because of that I have got this n minus 1 times un minus 1, all these things are coming into picture. To avoid this, make partial fraction expansion, P of e means partial fraction expansion of f of z over z and proceed. You get a similar set of answers here. But then whenever you have quadratic terms here and the poles are complex conjugates, then we know that this is associated with a sinusoid term in the discrete time function. Therefore, one can identify this with what would you expect when you have a damped sinusoid and then get at the solution in a much more direct fashion, and that's what I would like to proceed now. Show. Okay. So as a third alternative, we keep at the back of our mind that e to the power of minus n alpha sin n omega as the z transform z e to the power of minus alpha sin omega over z squared minus 2z cos omega e to the power of minus alpha plus e to the power of minus 2 alpha, and e to the power of minus n alpha cos n omega as the z transform z times z minus e to the power of minus alpha cos omega divided by same denominator. So this is the background that we have. Now in our case we have z upon z squared plus z plus half. So we have to compare this with either one of these expressions or a combination of these two expressions. After all, since the numerator we have only z, so it is we should be able to fit this with this particular expression. But if you have, for example, z squared plus z, we will have to think of a combination of these two. So comparing this with this expression, comparing this with x, we can see that e to the power of minus 2 alpha equals half. Therefore, e to the power of minus alpha equals 1 over root 2. And the denominator, you have minus 2 cos omega times e to the power of minus alpha, e to the power which is 1 over root 2, that should be equal to 1 because the coefficient of z equals 1. Therefore, cos omega equals 1 by root 2, minus 1 by root 2. Cos omega is minus 1 by root 2. Let us see the numerator. Numerator is z e to the power of minus alpha sin omega e to the power of minus alpha sine omega, we possibly, what we may have is some k times this, so say let us say a times this, a times e to the power of minus alpha sine omega happens to be equal to 1. Therefore, a times e to the power of minus alpha is 1 by root 2, and if cos omega is 1 by root 2, the magnitude of sin omega is also 1 by root 2. Suppose you take sin omega to be 1 by root 2, this is equal to 1, therefore a equals 2. And if sin omega equals 1 by root 2 and cos omega is minus 1 by root 2, with omega will be 3 pi by 4. So that means sin omega is positive 1 by root 2, cos omega is minus 1 by root 2, so the angle will be 135 degrees, corresponds to 3 pi by 4. A is a constant. So that means we have, this is a times a quantity like this. Therefore, a, where a is 2. Therefore, f of n corresponding to this can be written as 2 times e to the power of minus alpha is 1 by root 2, but we are talking about e to the power of minus n alpha, therefore 1 by root 2 to the power of n sin n omega, that sin 3n pi by 4, and of course u of n. So this is the result which we had already obtained earlier, but we have now obtained this in a more direct fashion. So whenever we have complex conjugate poles, then it would be convenient to fit this in the given function with either one of these or both. Sometimes when you have a quadratic in the numerator, you may think of a combination of these two and try to fit the numerator so that it is an appropriate linear combination of the z transforms of these two functions. Let us take another example. As a third example, let us consider f of z to be z cubed plus 2z squared plus z plus 1 divided by z minus 2 whole squared times z plus 3. Obviously here you are having a repeated pole at z equals 2. So, and there is a linear term here. So let us put f of z over z. So you have z cubed plus 2z squared plus z plus 1 divided by, because we introduced a z here, z times z minus 2 whole square times z plus 3. So you have the partial fraction expansion, you have a upon z corresponding to this plus z plus 3, a term let us say b, and then corresponding to z minus 2 whole square you have a c, but since z minus 2 whole square is involved, you have two terms, z minus 2 and z minus 2 whole square, let us call this d. Now in this partial fraction expansion, a, b, c are easy to obtain. To get a, you multiply by z and take the limit of the function as z goes to 0. To obtain b, you multiply by z plus 3 and take the limit as z goes to minus 3 or value at z equals minus 3. To get c, you multiply this by z minus 2 whole square and take the value at z equals 2. So let us do that first. So a equals z cubed plus 2z squared plus z plus 1 divided by, you are multiplying this by z, therefore this disappears, z minus 2 whole square times z plus 3, then z equals 0. So that will be turn out to be, the value of a will be 1 by 12. Likewise, you can find out b in the same fashion. Take this z plus 3 out and substitute z equals minus 3, you will get b as 11 upon 75. C likewise can be obtained by lifting this portion out and taking z equals 2. Limit of this function, value of this function as z equals 2, that turns out to be 19 upon 10. To obtain d, you multiply this by z minus 2 whole squared and take the derivative of the remaining function and take z equals 2, just as we have done in the case of repeated poles in the continuous time situation, where in the Laplace transform case, whenever we have repeated poles, we said you multiply this by z minus 2 whole square and take the limit, take the derivative of this with reference to z and take its value at z equals 2. Much the same thing we do here. Therefore, d will be d by dz of the function that is obtained after removing z minus 2 whole square, that is z cubed plus 2z squared plus z plus 1 divided by z upon z plus 3 and evaluate this at z equals 2. So I will not do the complete work. You can show this to be 77 upon 100. So we have got all the partial fraction terms now, a, b, c, d. Therefore, f of n can be written as so I'm sorry. Now we have got this. This is a partial fraction expansion of f of z over z. So f of z can be written as 1/12 plus 11 by 75 z upon z plus 3, this quantity, plus 19 upon 10 z over z plus minus 2 whole squared plus 77 upon 100 z upon z minus 2. So that will be, from this you can get f of n 1 by 12 delta n, that means there is only one sample standing at n equals 0, plus 11 by 75, this will be z upon z plus 3 corresponds to minus 3 raised to the power of n un, then this will be 19 upon 10, this is z upon z minus 2 whole squared, therefore you are getting n times un, n times 2 to the power of n un, plus 77 upon 100 2 to the power of n un. So that's what it is. So that is the final expression for the discrete time function corresponding to the given f of z. Lastly, let us take yet another example. Let us take f of z to be z upon z minus 1 whole cubed. Now we will view this as the product of z upon z minus 1 whole squared and 1 upon z minus 1. So f of z is the product of two functions. We know the inverse Z transform of this, that is R of n. This inverse Z transform of this is u of n minus 1. Therefore, f of n is the convolution of the two corresponding time functions. The convolution corresponds to the product in the transform domain. Therefore, this is Rn convolved with u of n minus 1. Rn convolved with un minus 1. So let us see what this implies. You have Rn. So it will be like this. So this is k Rk. Now this has to be convolved with un minus 1. Un minus 1, uk minus 1 starts like this. This is uk minus 1 with reference to k, this is equal to 1, this is equal to 0. Now you fold it, that means it starts with 0 and comes like this, and you advance it by n units. Therefore, you have this is u of n minus k minus 1, where the nth sample is here, this is n minus 1. So what you are now doing is you are multiplying this out for different values of n and summing them up. That means you multiply this sample with this value, multiply this sample with this value, and so on. Therefore, whatever you are having here, this is equal to Rk summed up u of n minus k minus 1. Summation from k to 0 to n means you are multiplying these samples by these unit values and then summing them up. So for this particular situation, first n minus 1 samples are taken in the Rk and then summed up. That means you are taking 0, 1, 2 right up to n minus 1. And that will fetch you the answer n into n minus 1 by 2. So your f of n now is in this, as a result of this, can be written as n into n minus 1 by 2 un, because if n is negative, then it will be shifted in this direction and there will be no overlap of the sample, that is going to be 0. So whatever you are having here will be valid only for positive n. So f of n happens to be n into n minus 1 by 2 times u of n. So in this lecture, we started with the proof of the final value theorem, the statement of which was given in great detail, in full detail in the last lecture. And we said the final value theorem has certain restrictions. It will be valid only if 1 minus z power minus 1 multiplying by f of z has no poles either on the unit circle or outside the unit circle. We saw two examples illustrating the application of the final value theorem. Then we talked about finding out the inverse z transformation, that is to recover the time function, discrete time function corresponding to a given f of z. We saw that there are three basic ways: the contour integration method, the long division method, and the partial fraction expansion method. The partial fraction expansion method is the most suitable one for our needs, because we break up the given function into simpler functions which are easily recognized as the z transforms of known discrete time functions. This doesn't require any complex integration in the complex plane as in the contour integration. Also, we get closed form solutions which may or may not be available in the straightforward division case. And furthermore, the partial fraction expansion method is something which we are familiar with in the context of Laplace transformation theory, and therefore we saw how the partial fraction expansion method is useful to us by working out a series of examples where involving simple functions. And we said that whenever linear terms are involved, that is when the denominator has one pole in the various single pole terms in the partial fraction expansion, it will be convenient for us to make the partial fraction expansion of f of z over z rather than f of z. And when quadratic terms are involved, we may do it by taking the partial fraction expansion corresponding to two complex poles, or alternately you can associate this with the z transform of a damped sinusoidal function e to the power of minus n alpha times sin n omega or cos n omega, as the case may be. It is also sometimes convenient for us when we have got a complicated term to view this as the product of two functions and then use the convolutional principle to find out the associated discrete time function, as the last example showed. We will in the next lecture discuss some of the applications of the Z transform theory and find the solution for the difference equations using the Z transform approach.